This video lecture is about permanent magnets. The kind like bar magnets, they always have a north and south pole. And with two permanent magnets, opposite poles attract, so the north and south poles attract each other. And like poles repel, so if you put the north end of two magnets toward each other, they'll repel each other. And when two magnets are positioned this way, the magnet on the right will exert a torque on each other. Magnets come in lots of different shapes and sizes, such as horseshoe magnets. You can also get very thin magnets, but they all always have a north pole and a south pole. Now we talked about the Lorentz force and Ampere's law, and we're going to see now how the Lorentz force and the Ampere's law connect with these more familiar phenomena within magnetism. And we're going to see how the Lorentz force and Ampere's law actually explain these phenomena. So first of all, what is a permanent magnet? Basically, you have atomic orbitals that have some angular momentum. So that means there's a sense in which these atomic orbitals are going around the nucleus in a particular direction. And when we have electric charge rotating around the nucleus in a particular direction, then that's like it is an electrical current that is going in a loop. And that electric current going in a loop gives rise to a magnetic field that looks like this. And to simplify the drawing I'm about to make, I'll draw these current loops and the magnetic fields they create with just a simple black arrow pointing in the direction of the magnetic field at the center of the loop. Now, if we have a bar of such a material, such as iron, and all of the atoms are pointed in random directions, then all of their magnetic fields are pointing in all kinds of random directions and they cancel each other out. But when a large number of them are pointed in the same direction, those magnetic fields will add together rather than canceling out and produce a substantial magnetic field. And that is the magnetic field that we are familiar with, created by permanent magnets. The magnetic field lines form complete enclosed loops. And this end is the one that we call the north end, and this one is called the south end. Each atom is called a magnetic dipole, and when you put a bunch of magnetic dipoles together, you have a bigger and stronger magnetic dipole. So now let's consider the forces that two magnetic dipoles exert on each other. We'll start with two magnetic dipoles pointed in the same direction. The one on the right generates a magnetic field that looks like this. Here are the north and south poles of each labeled. Hopefully the 3D-ness is clear here. So let's now consider the Lorentz force exerted on this magnetic dipole on the left. We'll start by looking at the top of the loop of current. Here the current is going into the screen, okay, and the magnetic field is going up this direction. So using the right-hand rule, the magnetic force goes this way. It's at a right angle to the current goes into the screen, so it's parallel to the screen. It's in the plane of the screen. That puts it at a right angle to the current, and it's also at a right angle to the magnetic field itself, which we can see here. So that's good. Let's do the bottom now. Right-hand rule gives us a magnetic force going this way. Now the vertical components of these two magnetic fields are opposite, so they'll cancel. But the horizontal components will add to each other, resulting in a net magnetic force pointing to the right. Newton's third law tells us that the magnetic force on the right-hand dipole must be equal and opposite, so it points to the left, and so these two parallel magnetic dipoles exert an attractive force. Exactly as we expect from what we know from playing with magnets. Now, by similar reasoning, if the dipoles are pointing in opposite directions, then on the left dipole, the vertical components again cancel. The horizontal components of the magnetic forces are now pointing to the left, so the net force on the left dipole is to the left, and the net force on the right dipole must then be to the right. So they're repelling, so we've now explained another case that we saw on the first slide, where like poles repel each other. Now let's consider a case of magnetic dipoles at right angles to each other. Just to be clear about the third dimension in this dipole on the left, here the current is going into the screen, and here, out of the screen, and here it's going into the screen. The magnetic field from the loop from the dipole on the right looks like that, and the Lorentz forces on the leftmost and rightmost part of the magnetic dipole on the left are going to go in that direction, resulting in an overall torque that will try to rotate the magnetic dipole so that the south pole is closer to the north pole of the other magnetic dipole. So we've now explained the third case that we opened up with, where if you put magnetic dipoles at right angles to each other, they exert a torque on each other to try to align. So that's the torque for magnetic dipoles at right angles to each other. For homework problem 11, determine the net force that these two magnetic dipoles at right angle to each other exert on each other. Just the direction of it. So is the net force exerted on the left dipole by the right dipole A, upward, B, downward, C, leftward, D, rightward, E, into the screen, F, out of the screen, or G, is it zero net force?